Hello everyone, this is the midterm demo presentation of Group 18. In this presentation we will review the progress we have done so far and our expectations for the final demo of this project. The rain energy harvester is designed to generate power using the renewable source of rainwater. This system is intended to be installed with the gutter of a house or building so that it can take advantage of the water collected on the roof, where otherwise, on a regular gutter structure, the water will be dispersed on the ground level. The rain energy harvester consists of a pipe that will be connected to the gutter of the roof of a house, a turbine, a motor, and LCD screen to display the power generated. For the demonstration of this project, we'll simulate how the project will perform ideally connected to a single gutter. The following results and videos will be showing the regulator efficiency, turbine speed, and power generation that the rain energy harvester currently has. These three specifications will be the ones shown in the final demo of this project. For all of these requirements, we're expecting higher and more consistent results in the final demonstration. These specifications will be shown on the LCD screen as a result from the measurements of our sensors. Our system will have an USB outlet to provide power to small devices. The output requirement refers to the minimum current that we expect that will flow through the USB outlet. Lastly, these are the dimensions our system will have when it is fully assembled.
White PVC piping will be used to simulate a gutter. There is a jet nozzle near the bottom that will focus the water into the hydro turbine. The Pelton turbine has multiple paddles that are used to absorb the force from the jet of water and causes the turbine to rotate. There are multiple mechanical parts that will be used to connect the turbine and the motor for power generation. These mechanical parts were not ready for this demo, so we will have to test these parts separately. A waterproofed wooden casing will keep the turbine and the electrical parts separate to prevent any potential water damage, and will allow the connection between the turbine and the motor through the mechanical parts.
When the motor is spun, it produces a two-phase AC output through the wires. The single wire output was measured when hand cranking the motor. The AC output is shown on the slide. The full bridge rectifier converts the AC input from the motor to a DC powered output. There are two full bridge rectifiers connected in series, each rectifying one phase of the motor. When the motor was hand cranked, the DC output voltage was measured to be at average 20 to 40 volts.
Here you can see we breadboarded the output voltage regulator, which is able to regulate the output voltage down to 5 volts in order to power a USB 2.0. On the RMS multimeter in the top right, you can see we hand crank the motor and it regulates to around 5 volts. And we also measured the current using a DMM with a 100 ohm load and got about 34 milliamps as the current. But we expect to get the current we need to power USB devices, which is about 0.5 amps, using an actual using our actual setup instead of hand cranking. Here you can see the breadboarded supply voltage regulator, which will be mainly powered by a 9-volt battery and will provide power to the sensors, MCU, and LCD. We measured the battery before using it, and it was about 9.43 volts, and then we connected the DMM to the output and got that the voltage regulator was getting about 5 volts at the output as expected.
The rain energy harvester will have two sensors measuring the input voltage and current and the output voltage and current going to the USB outlet. Through multiple tests with constant power supply and with hand cranked input, we found these sensors to be accurate regardless of the consistency of the input.
Our MCU, the ATmega 328P, stores the values measured by the shunt sensors and displays these measurements on the LCD screen. This information can be displayed in a line graph form or in a more detailed text form, and a button is used to toggle between these two display modes.
So here we've got the light strip demonstration where we hand crank the motor to light up an LED strip. And here from the video, you can see that the lights are actually blinking. And that's because currently we have an inconsistent RPM. And we expect to have a more constant output when we get our actual parts, such as the shaft. And here we have the demonstration for our circuit powering a wireless charger, but unfortunately, when attempting hand cranking to power the charger, it was not working very well, so we decided to replace the motor with a 7-volt 0.5 amp constant source to show the minimum power values we need to power this device. However, we expect with a constant or a better, more constant RPM, we'll be able to power it in the final. And here's the demonstration for our handheld USB fan connected to the circuit. And again, we tried hand cranking, but it wasn't functioning here either, so we also did a 7-volt 0.5 amp source.
And then he can show off the screen too when you get done with that. Just show that it's accurate.
For the output power and regulator efficiency specifications, the LCD values were recorded while having the LED stripped as load and hand cranking the motor. From the LCD screen, intervals of voltage and currents were taken and multiplied to obtain the output power. The output power was very low, averaging 37.78 milliwatts under the midterm demo constraints. We expect to reach the power output specification goal of 2 watts or more in the final demo when the motor is connected to the turbine. Here is the line graph of the output power. The output power seems to be inconsistent, and that is most likely due to the varied rotational speed when hand cranking the motor.
So here we've got our output regulator efficiency measured by comparing the input of the regulator to the output, which more specifically means the raw DC signal coming out of the rectifier versus the regulated signal after the rectifier, in order to tell how well our rectifier or our regulator is functioning. We got the values on the left from the specification demo video and graphed it to show the efficiency trend. So the efficiency we were aiming for was about 50% or more according to our engineering table. By taking the average of all these values, we find that the regulator efficiency is 51.95%. So even without having our Mechanica parts, we've met our projected requirement. Also, when demoing our sensors, they were unfortunately not reading every value at the same time. So some measurements would update to the next time interval before, which is why you can see there are some inconsistencies on this graph instead of being a constant graph, such as the first 2 points, the 52.33%, which drops down to 14.42%. But now we fixed the code for future demos in order to reach and display every value at the same time.
Here we are measuring the approximate RPM of the turbine when there is no load attached to it. As you can see from the multiple readings, we are getting RPM values between 410 and to 460 RPMs. Once we install the shaft and other mechanical parts, we're expecting lower RPM values for the turbine because it will have a load when the shaft will be connected. It is also worth noting that the turbine was not perfectly set in the right position when doing this midterm demo. Due to these conditions, some speed was lost during testing, so the maximum turbine speed can be higher than the 460 RPM value. In the video, you can also see the pipe and the turbine chamber that is separated from the electronic casing on the other side. Here we have the data for the turbine speed during this test. The tactometer reads the RPM every 0.8 seconds, and as you can see, the turbine speed was mostly consistent throughout this demo. After 2.4 seconds, you can see that the RPM started decreasing, and it was most likely due to the turbine moving slightly during this demo. From these results, we had an average of RPM of 440. Even after installing the mechanical parts, we still have more than enough to meet our 150 RPM for turbine speed requirement or more.
So our remaining complications and challenges include the overall accuracy testing, because we didn't have our shaft when doing the midterm demo, so the values we measured in the specifications were all essentially approximations, since we're hand cranking the motor. Also, we need to get our final PCB, assemble it, and test it, which shouldn't be a problem since we've already breadboarded each part. Next, we need to find a good way to keep our pipe standing without having to hold it or lean it up against anything. And finally, we would like to find more low power devices we can use to demonstrate the functionality of our project.